Chapter 18, Thermodynamics, take 437,787. Maybe this time it'll work. So, in Gen Chem 1, we learned all about thermodynamics, except we left out the entropy part. So, we only discussed enthalpy and heat transfer. And according to the first law of thermodynamics, we should be able to have a perpetual motion machine, because the change of enthalpy of the system plus the change of enthalpy of the surroundings is always equal to 0, right? Heat only gets transferred, or energy only gets transferred from one system to another. This also implies that the change of enthalpy, I'm not doing another take. Enthalpy of the universe is 0. So we could have water that by gravity will go down, spin a turbine, that energy is converted and can help bring the flow back up, and we could keep going and going indefinitely. However, there's a second law of thermodynamics that deals with entropy, and the symbol is S, and the units are in joules per Kelvin. That's also important. And unfortunately, the change of entropy of the universe is positive. So that means there is an increase in entropy over time. And so every time we are, for a system like this, what this means is that every time we convert an energy from one form to another, there's an increase in entropy. So we lose there. So in order to and another example is just a coal-powered power plant, or whatever you use. Could be any source of energy, could be nuclear, but there's always a heat tax, we call it. So there's a tax when you convert the coal potential energy to thermal energy to heat the water here. Then there's another tax when you use the steam in the turbine, and then you send it to the grid in the form of electrical energy. So there's a tax every time, except in this case, we don't use that tax to fix the potholes. It's just lost money, or entropy is lost, and so we're just the big losers here, right? Anyway, you get the idea. Entropy is an increase in randomness or disorder, and so for any chemical process or chemical reaction or physical process, there's the question of spontaneity. Is this process spontaneous? Is this reaction spontaneous or not? And it's not just the enthalpy that matters, right? So enthalpy, we know that thermodynamically, enthalpy, if we have a change of energy, it's enthalpy favorable, right? So that means if the change in energy is negative, that's as far as enthalpy is concerned, a favorable reaction. But we also have this entropy, this change in entropy. So if the change in entropy increases, then we're in business. It's spontaneous, whichever way we look at it. And I'll revisit this in a second, but for now, you can probably understand that a beautiful car like this, given some time, will eventually spontaneously decompose, or it's gonna rust. The paint's gonna flake off, and this is going to rust. And this is a slow process, you might think, but it's still spontaneous. Now, slow and fast are not thermodynamic terms. They're kinetic terms. So they're completely independent from thermodynamics. But from a thermodynamic standpoint, this should be a favorable reaction. Okay? Not a favorable, but a spontaneous reaction, because both has an increase in entropy, and it's exothermic. Now, as I said, things get a little bit more interesting when we have, for example, an exothermic system. So it's enthalpy favorable, but we have ordering of the system. So we have a decrease in entropy, so then we have a little competition here, but there are ways to determine if something is still spontaneous or not. The only scenario where it's never spontaneous if we have an entropy decrease, so more ordered system, and we have an endothermic reaction, which means an energy input. So this plus minus situation is a no-go. That would be non-spontaneous. Okay, so which is the case here. Looking at an energy diagram, it has both the kinetic and the thermodynamic aspect shown. As far as thermodynamics is concerned, we only are looking at the increase or decrease or the change in energy of the products versus the reactants. In this case, this is an endothermic process. Energy is input, and the kinetic aspect is this, right? So from thermodynamics, we don't care how large this increase in energy is here, right? This is just the energy of activation, but we do care about that as far as kinetics is concerned, because that'll tell us how fast the reaction is. And so if we are able, you recall, a catalyst will lower the energy of activation, so that's how we can speed up certain reactions. So, but this chapter is not on kinetics; it's on thermodynamics. So all we care about is the change in energy of the reactants and the products, or the initial state and the final state. Just to drive this kinetics point home, here the conversion of diamond to graphite is enthalpy favorable because delta H is negative. It's also entropy favorable. Delta S is going to be positive here. We have more randomness or chaos or whatever you want to call it going from diamond. Diamond is more ordered than graphite. So every time we go from a less ordered system to a more ordered system, and that's how you should probably think about it, because you can then think about, okay, if any kind of heat increase, like if we're melting or we're boiling, this is going to be an increase in entropy, so this is entropy favorable, or there's an increase in entropy, rather than thinking about it the physicist way, like Ludwig Boltzmann, whose definition of entropy is a thermodynamic function that increases as the number of energetically equivalent ways of arranging the component increases. S. Okay, this S is your entropy here, and then he uses energetically equivalent ways, and if you have more energetically equivalent ways, then you have more chaos, and that's all we really need to know. And then of course he's loving him a nice little equation here. We will not be using that equation, but it is important to note that we have some sort of constant, and that's Boltzmann's constant, like the ideal gas constant divided by Avogadro's number here, right? And then W is not work. W is just the number of energetically equivalent ways a system can exist. And I do want to address that for just a second, just because it's a challenge for me, and I like a challenge. So let's see how I do. And if I don't do very well, and you really want to know what this energetically equivalent thing is, there's great videos out there, right? All right, so what does Onkel Ludwig mean by this? All right, so I'm going to give it a shot. Remember kinetic energy, average, we looked at average kinetic energies, and so we said that there's an average, but there's also some particles that have lower energy and some particles that have higher energy. So there's a distribution of different speeds, and then there's an average. And this is very similar, these dispersal modes here, right? So imagine a glass tube that's connected to two containers, and there are 4 particles in there, and so there's exactly 4 positions that these particles can be in. And then once you open up that valve, they can disperse. And so there are possibilities here, right? One possibility is that these 4 particles will stay put. That's one possibility, and within that possibility, we call that a microstate. There's only one microstate because there's only one possibility to put those 4 on the left. This would be the 4-1 scenario. There's another macrostate or possibility that all 4 of these particles will go to the right. So we would have the reversal of that. Would be this is 0, of course. 4 and then 0. 0 and 4. This would also have only one microstate. And then we can have the scenario where we have 1 coming over here and 3 staying put. So this is the 3-1 possibility. That is the macrostate. Now within that state, there are more than one possibility to arrange those, right? So you can have 3 here and 1 down, and so you have more microstates, right? So that's more likely to be the case. So statistically, it's more probable than the 0, 4, and the 4, 0 possibility. And then you can also have the the 1, 3, and those have identical statistical probabilities. And then the one that, of course, leads to the most microstates is the one that we would intuitively go to, right? I mean, these two are going to spread out, like this, somehow, 2 here and 2 there. And so this is at some equilibrium. We would expect that to be the most likely scenario. Sure, we could they go back and forth, right? There's diffusion going on, so we may have some of this. But the bigger point here is that this is the microstate. This is the macrostate that has the most microstate, or most of the energetically equivalent states, and so this is has the highest entropy. At least this is how I look at it, and this is how I understand it. And so here's just different possibilities of distributing microstates and macrostates. All right, moving on and do something more useful. Gosh, I'm going to be like stoned by all the physicists that are still alive for saying that that is not useful to look at energetically equivalent states. But I'm just going to go out on a limb and argue that no physicist will ever watch this lecture. So, all right, we can easily determine whether a system or a reaction or a process has an increase of energy, an increase of entropy. For example, dissolving a solid, that's got to be an increase in entropy, right? Especially if it's ionic, and we go from sodium chloride here as a solid to sodium ions. That's a dispersal of energetic states or particles, right? So we go from 1 particle to 2. That's an increase in entropy. You can just do that for any reaction. You count the molecules on the left and the molecules on the right, and if that number goes up, you have a positive entropy. If that number goes down, you have a negative entropy. So that's one way to look at it. You can also look at phase changes. For example, going from liquid to gas. Any liquid to gas requires energy input, which will result in a dispersal of energies or a dispersal of particles or an increase in randomness. So highly ordered, less ordered. So evaporation and melting are both an increase in entropy. And since we're here, you also know that evaporation, which requires a heat input, is an endothermic process. So thermodynamically, or enthalpy, is not a favorable process. So we already run into this problem of entropy competing with enthalpy, whether something is spontaneous or not. We'll get to that in a second. Let's practice just looking at some of these reactions here. So going from gas to liquid means we have a more ordered system. So we're going to have a negative entropy. Sublimation means we're going to have an increase, right? We're going to stick energy into it to sublime, go from solid to gas. And then here we count 2 going to 3. So that's also an increase in entropy. So you can practice this a little bit. There are explanations here if you want to read them later on. And then there's stuff for you to practice. But I got some more because I have it and I like it. So liquid to gas, increase, right? Solid to gas. Oh, that's not how we look at it, right? We look at the number of particles here, right? Oh, you could possibly argue here. We go from solid and some of it is gas, so maybe based on that. But no, you just look at 1 going to 2. That's an increase in entropy. 3 going to 2. That's becoming more ordered. Here we have 3 going to 5, this order is increased, and here we have 2 going to 2, so no increase or decrease in entropy. All right, fair enough. we can use an equation, and this is obviously provided, to calculate the change in entropy of a process or a reaction. So here we're looking at phase changes, as you know, here they are listed. What do we have? We have the delta H of vaporization, and we have just the delta H of vaporization. So we're just boiling here. But we also know that the reverse process, condensation, would simply have a negative sign, right? From a thermodynamic standpoint, Q here, thermodynamics, right? And so the change in entropy is equal to Q enthalpy reverse, right? So if I read this real quick for you here, they want you to calculate the entropy of a system. You're given 25 grams of water, so we know it's water, and we're going to condense, right? So we know that condensation is going to be exothermic. We're going to have a release of energy, but we know that the entropy system has to be positive, right? So that's why it's Q reverse. And so if I were to do this here, and this is in kilojoules per mole, so I got to do a couple things. I have to do the 25 grams and multiply it by 1 mole divided by 18 grams, and I get some sort of moles, and then I have to apply that to the energy here. But let's just do that for 1 mole first. So delta S, and we're talking about condensation. So condensation would be negative, but so negative 40.7, and the temperature, of course, is 100, so it's 373 K. And you know, if you get messed up with those signs, you can probably just think about it, right? So it's asking for the entropy of the system. I know it's getting really cluttered up. So the entropy of the system, of course, if you are going to condensation, should be negative. So we know this is negative, right? So using negative 40.7 kilojoules here happens to work out, okay? So this gives us some number, but as I said, we also need to convert that to moles, and so whatever that number is, we then apply that to the number of moles, because this is going to be in joules per K. Let me just bring it up here, right? So here we are converting grams to moles, and then we're applying, he does it all here in one, and he divides by the temperature, and that gives you an entropy of minus 151 joules per K. As I said, the units of entropy are in joules per Kelvin, in contrast to the units for enthalpy, which are just in kilojoules or joules or sometimes per mole. Okay, we can apply that same equation to a chemical reaction, and so instead of Q, you just have delta H, right? So here we have a combustion reaction. We can look at that. We know we have an exothermic reaction. So we know that the entropy of the surroundings is going to increase because heat's going to be given off, which will cause entropy to increase. We can also look at the combustion itself. So we have 5 moles of oxygen and 1 mole of propane here. So that's 6 particles, or 6 moles, going to 7 moles, since I started with moles. So we also know that delta S for the system is going to be positive, okay? So delta S of the system and delta S of the surroundings is going to be positive, right? Because this is going to cause that to go up. So it's useful to me to just look at this and think about just the signs that we're going to expect before I do any kind of calculations, right? So my first question here is calculate the entropy change of the surroundings. So that tells me it's going to be a positive sign. And I'm doing this reaction at 25 degrees. So it's the same delta S. And I'm going to do negative times a negative. So in this case, Q is going to be 2044. Or you just make that positive period because you know it, because you thought about that, divided by the temperature, which is 298 K. So whatever that is the answer to question A, and it needs to have a positive, no matter how you set this up here, right? So if you calculate, if you didn't do this negative here, and you plug the negative, and you got a delta S that's negative, then you should at least think about it and say, hey, no, that's not true. The surroundings have an increase in entropy. Determine the sign of the entropy change for the system. Okay, so for the system, we already did that. That's going to be the 6 moles going to 7 moles, so this is also a plus. And then C is determine the sign of the entropy change for the universe. Did that already before we even read the questions, right? So the system as well as the universe, the change in entropy of the universe is always positive. So at least that's how I see it. So there's no other answer here. If we're talking about the universe, always up, right? But the question about is this reaction spontaneous goes back to what I said earlier about enthalpy and entropy. So it's enthalpy favorable and entropy favorable. And for that, we need to look at, of course, the system, okay? And yes, so delta H is negative, delta S is positive. This is for the system. So this is a go. Here is the cleaner mathematical equation here, and I have an actual result. So again, positive, and you know, that's enough for lecture 1. More fun in lecture 2.